Welcome to the Explainer. Let's just dive right in. If you work in robotics, you already know all about the shared trauma of hardware integration. I mean, we've all been there, right? The late nights, the sudden, inexplicable regressions, those mysterious bugs that only seem to pop up the second your software touches actual metal. It's brutal. But what if I told you that building a truly robust CI/CD platform, a continuous integration and continuous deployment pipeline is literally the ultimate solution to all that pain? Today, we're walking through the real hard-earned lessons from building a ROS2 software-in-the-loop CI/CD platform completely from scratch. We're going to see exactly why the pipeline is the thing that actually keeps your hardware safe.
And honestly, that brings us right to our starting point here. Do you know how we all sit around and swap these integration war stories? We kind of laugh about the time the robot just went completely rogue, or, a bench literally caught fire. Well, here's the raw truth about that. Those ubiquitous robotics war stories, they're actually just process failures wearing a costume.
Take a look at this quote right here, because it perfectly captures the reality we live in. Every robotics engineer I know has a story about a small change that bricked a robot on the bench, a merge that silently regressed a controller, or a release that worked on one machine and failed on its twin. We've all seen it. A so-called small change completely bricks a robot and just vaporizes precious bench time. The integration pain we feel in this industry is real and it is endemic. It's not just theoretical, but the whole point of this project, building the AutoNav SIL platform, was about taking that specific, very real pain and turning it into a concrete, reproducible solution. So here's our roadmap for this explainer. First, we'll look at the real integration pain. Then we'll cover process, discipline, and decisions. Third, we'll dive into the technical lessons for CI/CD. Fourth, we'll talk about culture, trust, and team speed. Fifth, we'll look at future-proofing and next steps. And finally, we'll wrap up with how the pipeline ultimately protects the robot. All right, Section 1, the real integration pain, moving beyond theory. And we really are moving beyond theory here. The platform we're talking about today isn't some pie-in-the-sky vision deck or an academic white paper. It is a concrete repository that acts as a literal gate before your code ever gets to touch real hardware. Now, let's look at the core thesis. Simple robot, production-grade pipeline. You'll notice that the AutoNav robot is pretty basic. It's a differential drive robot with no nav2, no SLAM, no ROS2 _ control. But honestly, so what? The actual complexity of the robot matters way less than the pipeline that's validating it. The overarching goal here is simply that every single code change is thoroughly tested, traced, and shipped safely. The pipeline's value is completely independent of how complex the robot itself happens to be. Moving on to Section 2, process, discipline, and decisions. Because yes, scope discipline is absolutely a feature. When you're engineering a reliable integration pipeline, scope discipline isn't just some annoying constraint. It is a core feature. Knowing exactly what not to build gives you a massive advantage. And how do you maintain that discipline? Well, you use something called an ADR, or Architecture Decision Record. Think of these as living documentation. The second a trade-off starts getting fuzzy, you write an ADR. It forces you to capture all those rejected alternatives at the exact moment the decision is actually made. So later on, you can just read the commit to understand why a choice was made, rather than relying on some retroactive blog post written 6 months down the line that pretends you knew the right answer all along. And ADRs are what help you stick to your phase plan cut lines. Let me tell you, a strict phase plan will absolutely save your project. Before you even write a single line of code, you have to define the non-negotiables. We're talking things like the hardware abstraction layer boundary, sim time, the merge queue, the SIL gate, and strict traceability. Then, you clearly define your negotiable stretch goals, your cut lines. Because when time inevitably runs out, these cut lines tell you exactly what features you can safely drop, things like multi-arch builds or noise injection, without having to relitigate the entire project scope. All right, Section 3, technical lessons for CI/CD, the mechanics of safety. So let's dive into those mechanics of safety. How does wiring every single layer, from linting all the way to release, actually work in practice? Well, this summary grid lays out the structural choices that give you a truly deterministic foundation. First up, the HAL boundary. This acts as the absolute heart of sim to real. You swap one box, and the entire software stack stays identical. Then there's sim time, which gives us a deterministic CI foundation. That means absolutely no sleep commands allowed. Next, look at the merge queue. This enforces retesting against the latest main branch, essentially putting an end to the whole "it broke on main" excuse. For a traceable release, it's a clear chain, digest to tag, to commit, to PR, to issue. The golden rule here? Test what you ship and test the tests.
In a system like this, every single bug you encounter just equals a missing check.
And all those checks? They're structured into this, the 4-layer test pyramid. Your code has to pass every single gate in this exact order before it even thinks about touching the physical robot. It kicks off with linters, then moves to unit testing with G-test, then basic smoke tests, and it finally culminates in a full software-in-the-loop or SIL run against a simulated vehicle in sim time. It's basically an impenetrable sequential safety net, where each distinct layer catches a completely different class of failure. Section 4. Culture. Trust in team speed. This is the human element of CI/CD.
A truly reliable technical pipeline doesn't just change your code, it fundamentally changes human behavior on your team. The crucial takeaway here is that a robot is not a web app. If a web developer says, hey, it works on my machine, it's usually just a minor annoyance. But in robotics, a bad merge can physically damage thousands of dollars of hardware, it can injure a bystander, or it can burn through bench days that your team simply cannot afford to lose. Validating every single change without needing the physical hardware is a strict safety requirement. It is absolutely not just a nice-to-have convenience.
And if you want that validation to actually mean something, you have to internalize this rule. Flaky tests erode trust, and they erode it fast. Once a test suite starts flaking, human nature kicks in, and your team just starts ignoring it. And once they ignore it, bugs slip right through. The fix isn't to just hit rerun until it miraculously turns green. No way. The fix is having deterministic sim time and a hard, non-negotiable policy that flaky tests are immediately quarantined or they block merges entirely until they are fully resolved. Which brings us to this pretty harsh reality. Integration without a merge queue is basically just hope it works engineering. Think about it for a second. A green pull request at 9 a.m. means absolutely nothing if 3 other pull requests land before yours actually merges. The merge queue tests your code against the actual main branch that your change is going to land on. It guarantees stability instead of just shipping a probability. Moving to Section 5, future-proofing next steps, because the work always continues.
Even when the initial platform is done, the work goes on. But the beauty of a well-architected CI/CD pipeline is that it's explicitly designed to absorb planned expansions. Remember those cut lines we talked about earlier? Well, here are the documented stretch goals that were initially deferred. We've got migrating to a canonical RS2_control architecture, building multi-arch images for ARM64 embedded compute targets, adopting industrial CI conventions, automating dependency bumps with Dependabot, and even injecting noise into the SIM. Because of our strict discipline with those cut lines, these features are already perfectly scoped out. The pipeline is ready to absorb every single one of them without needing any massive restructuring. And finally, Section 6. The pipeline protects the robot, reevaluating the deliverable. We really need to rethink what the actual deliverable is for an integration engineering team. It's not about writing the smartest, flashiest algorithm. It's exactly this. The pipeline is what keeps hardware safe and teams fast. People constantly frame these two goals as a trade-off, but they are absolutely not. The exact same automated gate that protects your fragile, incredibly expensive hardware is the exact same gate that lets a junior engineer ship code safely on a Friday afternoon without needing some marathon review session. All that flashy autonomy and all those cool sensors, they are entirely downstream of the gate that decides whether any of that code actually gets to run in the first place. So I'm going to leave you with this final thought to chew on today. If a robust pipeline is the true deliverable here, the thing that fundamentally keeps your hardware safe and keeps your team moving incredibly fast, take a good, hard look at your own integration practices. What is your gate currently letting through? Thanks so much for joining this explainer, and I really hope this helps you build better, safer, and much faster robotics platforms.